All right, welcome everyone to the HMI 2022 Solutions stream. Thank you to everyone once again tuning in today, and also thank you for your continued support and participation in HMI. So today we'll be going over every solution to every problem on the 2 rounds, and we'll split it into approximately 3 blocks, and we'll have 2 short breaks in between. So firstly, we're going to cover about the first 2/3 of the individual rounds, and then after we come back from our break, we'll finish the individual round and the bonus problems. And then after another break in the last parts, we'll do all the team round questions together. So if at any time you want to rewatch previous solutions, feel free to pause or rewind. A full recording of the stream will also be published after the stream concludes if you want to rewatch any solutions then. And if you have any questions, feel free to ask at any time, and one of our problem writers will answer as soon as possible. With that being said, let's jump straight into problem number 1. So this is a straightforward question. If we just carry out the operations, we'll find that the answer is 1, 1, 2, 2, 3. Another way we can do this is we can pair up terms. So for example, 1, 2, 3, 4, 5 minus 1, 2, 3, 4 is just 1, 1, 1, 1, 1. And then likewise, 1, 2, 3 minus 12 is 1, 1, 1, and then 1 is just 1. So we can add it together like that. Okay, now moving on to number 2. So this is a question asking you to find the length of the green string here. And so we'll do it letter by letter. So firstly, on the H, we notice that we have 3 straight lengths. So we have the 2 vertical bars and the 1 horizontal bar. And so we can count the vertical bar. And so this is at a height of 9, and this is at a height of 1. So in total, the height should be of height 8. So the vertical bar here is 8, and likewise, the vertical bar along this side is also the same, so it must be 8 as well. Now, the horizontal bar goes from 1 to 5, so it must have a length of 4. And then another way we can count is to just count grid boxes. So the H in total must be 8 plus 4 plus 8, which is 20. On the I is very simple. It's just the same as one of these vertical bars, so it's also 8. Now the M is a little trickier. The vertical bars are the same, so they're 8 apiece once again. So the vertical bars together are 16, but now we have to handle these diagonal bars. So the way we can do this is through Pythagoras' theorem. So if we draw this right triangle, and it is a right triangle because the grid lines are right angles, we know that this is 3 and this is 4. And we also know that when a right triangle has legs of 3 and 4, it must have a hypotenuse of 5. And this diagonal bar must be the same thing. So it's 5 on this side as well. So together the diagonal bars are 10. So the H contributes 20, the M contributes 16 plus 10, and the I contributes 8, for a total of 54. All right, going on to number 3. Okay, so for number 3, there are a couple ways you can do it, but to do this one, I'll just do addition first and then do the division. So on number 3, let's do the addition first. And then now we'll divide. So we can do long division if you want, or if you have other methods to divide, that also works. So we can take out a 44, we can take out 2 here, which gives us 44, and 24, and then so on. And we can carry out this long division, and then at the end, we'll find that the remainder is just 20. And so we can confirm this by just seeing that 64, 24 is indeed divisible by 22. Okay, going on to number 4. So this is the first combo problem on the test, and so this is an independent arrangements problem. So here, the idea is that we can scramble these 6 different letters into these 6 different spots, and then find the total number of combinations. So in order to do this, let's assign a letter, let's say U, to the first slot. It doesn't really matter which one, right? We have 6 options for this first slots. Now, out of the remaining slots, we have 5 letters to choose from for this second slot. So let's say it could be B. And then we have 4 choices for the next one. And then there's 3 letters left for the next one, and then 2, and then 1. And then notice that all of these choices are independent. It doesn't matter what you pick in the first slot, you'll have 5 letters left over in the second slot, no matter what you do. So we can actually multiply all of these together. And when you do, you find that the answer is 720. Okay, moving on to number 5. So this is a word problem. So the first thing to break down is what the question is asking. So we have this judge who rules in favor of the defendant in 60% of the episodes in season 1. So season 1, defendants, 60%. In season 2, only 40%. And then in total, 50%, or half of the cases. We know season 1 had 15 episodes. And season 2 has some number of episodes, which is what the question is asking for. Well, in total, then, there must be 15 plus X episodes. Season 1 plus season 2. Well, let's look at the total number that the defendant won in season 1. Well, this is 60%, or 3/5 times 15, which is 9. And for season 2, this is 2/5 of X. So this is how many cases the defendant won in total. And over here, this is 50%, or half of 15 plus X. So if we solve this equation, we can expand the right side first. So we have 15 halves here, and X over 2 here. And 2/5 X here, and 9. So if we move stuff around, the numbers on this side become 3 halves, because 9 is just 18 halves. And then on the right side, the X's become 1/2 X, or 50%, minus 40% X, which is 10% X, or 1/10 of X. And then from here, if we multiply both sides by 10, X becomes 15. So season 2 must have had 15 episodes. Another way we can see this is, well, the defendant got 60% in season 1 and 40% in season 2, but 50% across the 2 seasons. So if the average was 50%, and 50% is right in the middle of 60 and 40, then the 2 seasons have to have equal weighting or the same number of episodes. So we can shortcut and say X is 15. Okay, now moving on to number 6.
So problem 6 asks us to find how many more hours Ling Ling has practiced over 5 weeks than Alex. So first we can find the number of hours Ling Ling practices every week. So since she practices 4 hours each day over 1 week or 7 days, this gives 24 times 7, or 168 hours in a week. And Alex practices for 4 hours a day on weekends, so this is 4 times 2, 2 hours on the weekends, since there's 2 days, Saturday and Sunday on the weekends, and 1 hour a day on the weekdays. So that gives an additional 5 times 1 times 5 hours this week. So in 1 week, Alex practices 8 plus 5, or 13 hours every week. And so over five full weeks, Lingen has practiced 168 minus 13 times 5 hours. And you can just calculate this to be 775 hours.
Okay. For problem number 8, uh, yeah, let's move on to problem number 8. Sorry, problem number 7. My bad.
So problem number 7, we have a triangle with, and we're given the measures of their exterior angles. So if we draw out the triangle, we're given that this angle is 3x, this angle is 236 degrees minus 4x, two degrees minus x. So we can either find the use that a triangle's interior angle plus its exterior angle add up to 180 degrees to find the measures of the 3 interior angles, or we can notice that the sum of these 3 exterior angles all add to 360 degrees. So if we write the expression for the sum of these angles, we have 3x plus 236 degrees minus 4x plus 162 degrees minus x, and this is equal to 360 degrees. And so now we can solve for x. So if we combine the terms of x, we have minus 2x plus 398 degrees equals 360 degrees. And so now we can find that x is equal to 19 degrees. And now we can just plug this into each of these 3 values. So we get 3x is equal to 57 degrees. 162 degrees minus x is equal to 143 degrees. And 236 degrees minus 4x is equal to 160 degrees. So if we want to find the measure of the largest angle of the triangle, we can also find the measure of the smallest exterior angle and subtract that from 180 degrees. So clearly the smallest exterior angle is 57 degrees, so the measure of the largest angle is just 180 minus 57 degrees, or 123 degrees.
Okay. For number 8, this is a independent probability question. So the idea is that we have 3 people and they all have an independent probability associated with them. There's a 2/5 chance that they're paying attention to the door, and so we want to know that at any given time, what's the probability that none of them are paying attention, so that they'll all be caught by surprise. And so we have to calculate the complements. So if the probability that they are paying attention is 2/5, then the probability they aren't paying attention must be 1 minus 2/5 or 3/5. And so in order for all of them to not be paying attention, the probability is 3/5 times 3/5 times 3/5. And so this is just 27 over 125. Okay, number 9. So number 9, we start with a number 326. And then so the first thing we do is we add 5s to the end of the number until the number is a multiple of 3. And so the first thing to do is, evaluate the 5s. So let's just check, is this divisible by 3? And well, we can find that the sum of these digits, 3 plus 2 plus 6, is 11. And 11 is not a multiple of 3. So obviously we need to add a digit. Well, now the sum of the digits is 16. And 16 is still not divisible by 3. So let's add another 5. So adding another 5 means that the sum of the digits is now 21. And 21 is divisible by 3. So using that divisibility rule, we find that 32655 is divisible by 3. So now let's check for divisibility by 11. So the divisibility rule for 11 is to take alternating digits. So basically, if you have like 1, 2, 3, 4, you add 1, and then you subtract 2, add 3, and then subtract 4. And then you'll have some sum over here. And if the sum is like 0, 11, 22, or like negative 11, or negative 22, etc., then it is divisible by 11. So let's use that trick here. So 3 minus 2 plus 6 minus 5 plus 5. Well, what does that sum give us? That gives us a sum of 7. Well, a sum of 7 is not divisible by 11, so we need to add another 7. Now let's try divisibility rule on this. 3 minus 2 plus 6 minus 5 plus 5, and then minus 7. Well, this sum is actually 0, which is divisible by 11. So our final result, 326,557, is what is left on the board. Okay, number 10. So 16 years ago, Jacqueline was half the age of Justin. In 5 years, Jacqueline will be 2/3 times the age of Justin. What is the sum of their ages in years? Okay, so this is an age word problem, a pretty kind of classic problem. So let's set up a system of equations. So let's let Jacqueline be A. Let her current age be A. And Justin's current age be B. So 16 years ago, Jacqueline's age was A minus 16. And this was half the age of Justin. Well, Justin at that time had an age of B minus 16. Okay, now let's look at the second statement. Jacqueline will be 2/3 times the age of Justin in 5 years. Well, in 5 years, Jacqueline will be A plus 5 years old. And her age will be 2/3 the age of Justin, which is, B plus 5. So now we can reduce these equations and then we can solve them. So first thing is on the left side, we'll multiply both sides by 2. So 2A minus 32 equals B minus 16. And so 2A minus B equals 16. Then for the second equation, we can multiply the left side by 3. So 3A plus 15. And then we'll distribute the 2 into the right-hand side. So 2B plus 10. And so move the letters to the same side. 3A minus 2B equals negative 5. So now we can try and cancel something. Let's multiply this equation by 2 on both sides. This gives us 4A minus 2B equals 32. And so now we can take this second equation and subtract the first equation from it. So this gives us A And then the minus 2b's will cancel out to give 37. 32 minus negative 5 is 37. So now we can plug back in. If a is 37, we can use this equation. For example, 2a minus b equals 16. So 74, which is 2 times 37, minus b is 16. So b must be 58. And so the sum of their current ages, a plus b, has to be 95. Okay, moving on to number 11. So in this problem, we have two different scenarios where a square is being rotated. And so the first thing to note is whenever something rotates, so for example, we have our unit square. Whenever something rotates in a complete circle, only the outermost edges will end up actually sweeping stuff. So pardon my bad drawing, but basically the outermost points, and you can test this on your own if you cut out a piece of paper and then spin it, the area covered will be a circle formed using the radius that is the outermost point. And so from the center of the square, the outermost point is actually any of its corners. And so if we sweep it out, this is the area of the circle. So this is scenario A. Now let's look at scenario B. We have the same square, but now we're sweeping it around a corner. So our pivot point is now here. While our furthermost point is here, the other vertex, which is diagonally opposite. And so it now will sweep a circle. But that circle, as you can see, is much larger because this radius is larger than this radius. And so we can see that this the radius here in scenario B has to be twice as long, right? Because this goes from the center to the edge, as center to the corner, and this goes from the corner to the center to the corner. So in total, this radius is twice as large. We know that because the area of a circle is pi r squared, if the radius doubles, you'll quadruple the area. So that means the area of B is 4 times as large. So the ratio of A over B has to be 1 over 4. And for this problem, we also accepted alternate forms. So 1 over 4 was acceptable, and 0.25 was also acceptable. Okay, going on to number 12. So again, we have another probability question. So Ashley and Michelle each choose a day of next week to go to the mall independently and at random. What is the probability Ashley goes on the day before, the day after, or on the same day as Michelle? So if we imagine our week as kind of this box with 7 partitions, 1, 2, 3, 4, 5, 6, and 7. If Ashley goes here, then Michelle has to go either here, here, or here. And so we would say, oh, well, there's 3 possibilities wherever where Michelle can go. So the probability is just 3/7. The issue is, what if Ashley goes on Sunday or Saturday? So if they go on the one of the ends of the week, well, then Michelle actually has 2 options. So these are the special cases. So let's deal with Ashley first. Let's say she goes to one of these days, 5 out of 7. Well, Michelle will have 3 options, right? Because there's no boundary to cut off the week. So Michelle will have a 3/7 chance of being consecutive or on the same day. And so this case gives us 15 over 49. The next case is Ashley going on one of the end days. So this is 2/7. And you can note that 5/7 plus 2/7 is our entire scenario. So we've covered all the cases here. 2/7 times, well, Michelle will only have 2 options, right? Either the same day or the day next to it. The day before is not an option here, and the day after is not an option here. So this gives us 2/7. So this case gives us 4 over 49. These cases are independent, so we can add it up. to get 19 over 49. Okay, moving on to number 13. All the students at Cottom Academy are going on a field trip. There are 336 graders, 398 7th graders, and 245 8th graders who will all be put in groups with people in the same grade. Ms. Cottom notices that for all 3 grades, if each group has exactly n students, then there will be exactly m students left over. So that means that if we divide 330 by n, 398 by n, and 245 by n, the remainder will be m for each group. And so we can actually rewrite these numbers. So let's say the 6th graders first. So if we have 330 students, let's say we have, I don't know, G number of groups. Well, G groups, in each group has n students. That's the total number of students in groups in 6th grade. But there will be m students left over. Okay, now let's do the same thing for 7th grade. 398 equals G, well, we can't use the same G, so I'll just say G1 n plus m. And then finally, 8th grade is 245. And let's say G2 n plus m. Well, this m term is actually a little annoying for us. So let's try to get rid of the m. And so we know that we can cancel this out by subtracting. So let's say 398 minus 330. So second equation minus first equation gives us 68 equals G1 minus G times n. Okay, so now we actually have something here. So we know 68 must be divisible by G1 minus G, and it must also be divisible by n. Okay, so that's a useful fact to know. So, let's try repeating this procedure on equations 2 and 3, or you can do it on 1 and 3. So we'll do 1 and 3 here because the numbers are slightly nicer. So 85, so equations 1 minus 3, 85 equals G minus G2 n. Okay, well, so G isn't such a useful variable here, right? It's something we created just to rewrite these expressions. But we can notice that n is always an integer. So the same n has to divide this is the same n that must divide this. So let's think what 68 is. 68 is 4 times 17. 85 is 5 times 17. So while n can't be 4, right? Because if n is 4, it wouldn't divide 85. And it also can't be 5, because if it were 5, it wouldn't be able to divide 68. So n is probably 17. And the other option, of course, is n could be 1. But n can't be 1, right? Because if you have groups of 1 student, then there will be no students left over. But we know that there are some students left over. So n has to be 17. So actually, now that we found 17, we can go back and calculate m. So remember that m is just the remainder. So 330, when divided by 17, leaves a remainder of 7. Yeah, something plus 7 over 17. So m is 7, n is 17, so n plus m is 24. Okay, on to number 14. So 14 is telling you that there is some kind of geometric series and there are some conditions surrounding it. So let's try and unpack it. So we know that an octave has 12 steps, and increasing a note by an octave doubles its frequency. So that suggests if you go up 12 terms in your geometric series, you'll double it. So let's say we have an A here is our first note, and then 12 steps up. So if you go 12 steps up, if we say one step is just multiplying it by r, the common ratio r, then going 12 steps up is a r to the power of 12, right? Because you'll have 12 intervals in your geometric series. So that means you've doubled your frequency. So ar to the power of 12 must be twice of a. So we can cancel out the a. and find that r to the power of 12 is 2. So that means our common ratio r is 2 to the power of 1/12th, or you can write it as the 12th root of 2. So the highest note is 87 steps above the lowest note. So let's say the lowest note is B. If we go 87 steps up, that's B times r to the 87. And so this frequency is some number of times larger. Well, that number of times larger is just B times r to the power of 87 divided by B, which is r to the power of 87. So the problem is effectively asking for this in this kind of weird form. So let's plug in. We know r is this. So 2 to the power of 1/12th to the power of 87. We know we can also multiply this exponent in. So we get 2 to the power of 87 over 12. And we can actually split this up. So this is the power of 2, 7 plus 3/12ths, or 1/4. The issue is b can only be fractional. So that means we need to get rid of this number exponent. So we can write this as 2 to the power of 7 times 2 to the power of 1/4, which is 2 to the 7 is 1/28 times 2 to the power of 1/4. And lo and behold, we have our form now. A is 1/28 and B is 1/4. So our answer is 1/28 and 1/4. Because we requested a mixed number in this problem, we did not accept alternate forms as correct. Okay, moving on to number 15. So the following shape is depicted, and so we're told some things. So first, M is the midpoint of DE, okay? And then a circle with center M is tangent to segments B, D, and C. So it's tangent here, and it's tangent here. Circle A is radius 20, and M is congruent to it, so it also has a radius of 20. And so we want to find the total shaded area. So this diagram actually compartmentalizes this geometry question very nicely for us. So let's deal with the circles first. So if we piece it up like this, we have some circular parts. So we have a circular part like this, and then another circular sector like this. So let's think about what this is. Obviously, the one over here is half a circle. Well, the one over here, well, we know this is an equilateral triangle, so this is 60 degrees. And we know a full circle is 360 degrees. So this remaining is a 300 degrees. 300 is 5/6 of 360, so this is 5/6 of a circle. So we know we have 1/2 plus 5/6 of a circle, which is just 4/3 of a circle. So 4/3 of whatever the area of the circle is, plus the area of this square, and then plus the area of this triangle. So now let's try and break into the square. So we know the radius of the circle is 20, and we know that it's also tangent here. A tangent means that it's right angle. It has a right angle with the radius, so we can draw that's a right angle. Well, it's also true on this side as well. And so we can notice then that we actually now have a right triangle. And so even more amazingly, this is a 45, 45, 90 degree triangle, right? Because if we look at this angle, this is a square, so this must be 45 degrees. And in a 45, 45 degree triangle, we can copy this length over because the legs must have the same length. And so likewise, this must be 20 because this is symmetric. And if you aren't convinced of this, you can just draw this and see that these two triangles are the same. And so if this is 40, then this must also be 40. So in total, we now have a diagonal of 80. And if the diagonal is 80, then the leg here must be 40 root 2, right? Because the hypotenuse is root 2 times longer in a 45, 45 triangle. So now if the side length of the square is 40 root 2, well then its area is 40 root 2 squared, or 1600 times 2, or 3,200. Now, we know this side is also 40 root 2, so now we can handle the triangle. Well, in order to handle this triangle, let's actually generalize what the area of an equilateral triangle is. Let's say you have a triangle with side length 2s. Because this is a 30, 60, 90 triangle, the height must be s root 3. And the hypotenuse is 2s, and we can confirm this. Well, then the area is the base times the height. So the base is 2s, the height is s root 3. So 2s times s root 3, and we have to divide by 2 because it's a triangle, to get s squared root 3. Well, in this case, 2s is 40 root 2. So s is 20 root 2. So if s is 20 root 2, then the area of our triangle is s squared root 3, which is 800 root 3. Okay, so now we've got our square, now we have our triangle, let's do the circle. The circle is pretty easy. We already know that its radius is 20. So the radius of a full circle is 400 pi, right? 20 squared times pi. Okay, so the circle is 400 pi, and we already know what fraction of a circle we have. We have 4/3 of a triangle, 4/3 of a circle. So we just multiply it. We have 1600 over 3 pi. Okay, now we just add the parts together. And this is our final answer. Alright, moving on to number 16. And then so we'll have 2 more problems and then we'll go to break. So in this problem, we have an octagon and then there are bytes taken out of it, which are in the shape of circular sectors, as this diagram depicts. So once this diagram is drawn, what we can see is that the perimeter of the shape will look something like this. So it's kind of like this gear with rounded and flat edges. So let's see what the problem gives us. Originally, the octagon has side lengths of 1. So that's 1. But we know the circles have a radius of 0.25. So if we take 0.25 off that end, and another 0.25 off this end, that gives us 0.5 in total. Well, then that means the end result is 0.5 in the middle. So that means the straight lengths here are 0.5. And, well, there's one straight length along each side. So an octagon has 8 sides. So this number of straight lengths is 8 times 0.5, or a total of 4 meters. So now let's calculate the curved edges. So in an octagon, the angles are 135 degrees. Now, in order to calculate this, the formula is 180 degrees times n minus 2 over n, where n is the number of sides in the polygon. So we have 8, and n is 8 here, so we can just calculate this as 3/4 of 180. Okay, and that evaluates to 135. So 135, as we can tell, is 3/8 of a full circle. If it's 3/8 of a full circle, then we have 8 of these circles, right? 8 of these sectors. So let's put them together. We'll get 3 full circles, right? And it's kind of similar to what we did just in the previous problem. Those 3/8, instead of being area now, are just the 3/8 of the full circumference. What is the full circumference? Well, we know the radius is 0.25, and the circumference is the diameter times pi. The diameter is 0.5, so, well, the circumference is 0.5 pi. So we have 3 of these full circumferences times what the circumference is, which is 0.5 pi, and that gives us 3/2 pi. So we can add the straight lines together plus the circular sectors together, and we get 4 plus 3/2 pi. And for this problem, we also accepted 1.5 instead of 3 halves. All right, last problem, and then we'll take a quick break. So number 17. How many 3-digit numbers are there such that both the number itself and the 2-digit number formed by removing its tens digit are divisible by 7? So this problem was a little tedious, but you can make it quicker with a couple of shortcuts. So the first thing to note is that let's go backwards. Let's look at the tens digit and then try and construct hundreds. Let's look at the 2-digit numbers and try to construct 3-digit numbers out of them. So the 2-digit number has to be divisible by 7. So it could be 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84, 91, and 98. Okay, now let's start constructing them. So 14. Well, after some trial and error, we can find that 154 is the only value that works. And so if we want to adjust the tens digit, we'll have to either add or subtract 7. But fortunately, 5, if you add 7, it goes out of range. If you go subtract 7, it's out of range. So this is the only one for 14. For 21, we get 231. Now, if you wanted to add 7, you would go out of range again. And if you try to subtract 7, you would also go out of range again. So it doesn't work. And one thing here we can actually notice is that the tens digit decreased by 2. And so we can use this pattern to our advantage actually to keep computing those values. In 28, well, 28, if you notice, when we assert a tens digit, the only thing that's changing is the units digit. And the units digit is changing by 7. So it won't affect its divisibility. So in reality, 238 is the same value. Well, what about 335? 35, we can test is 315 works. And we'll notice that 3 decreased to 1 again. So our pattern is every time you change up your hundreds digit, your tens digit has to decrease by 2 to compensate. And you can prove this algebraically, but I'll save that for later, just in the interest of time. So 315 here, well, we have to check actually, because now we can add 7 to this tens digit. So 385. This is effectively adding 70, and since 70 is also divisible by 7, this doesn't change its divisibility. So 385 also works. Now 42, same thing. So instead of decreasing by 2 from 315, we'll decrease by 2 from 385. So we get 462. And 462 indeed works. Then 49, 469, same thing. We haven't changed the hundredths digit. 56, we get 546. 63, 623. And then we can increase by 7 here. So 693. And then we have 770 and 700, right? Because we can decrease by 7. And then we have 777 and 707. And then we have 854, 931, and finally 938. And so if we count this all up, we get a total of 17. Okay, so that concludes our first part of this stream. So we'll take a quick 10-minute break, and then when we come back, we'll finish the rest of the individual round problems, and we'll do the bonus questions as well. And then in the final parts, once again, we'll do all of the team questions. So once again, thank you for tuning in. We'll be back in 10 minutes. Okay, everyone, welcome back. Um, so we'll now continue with the remainder of the individual problems, and then we'll go into the bonus problems before going on break again. So we did have some technical difficulties in the previous round of problems. Those hopefully should be fixed now, so I'll hand it back to Olivia to continue our solutions.
Okay, so problem 18. So we're given that the product of two real numbers a and b is root 3 minus 1 greater than their sum, and we want to find the value of this expression. So first what we can do is we can take what we know and write an expression out of that. So we know that a times b is root 3 minus 1 greater than a plus b. And so we want to find a minus 1 to the fourth power times 1 minus b to the fourth power Sure. Okay. And since we see that these two terms are both raised to the fourth power, we can combine them into a minus 1 times b minus 1 to the fourth power. Since in this case, we are allowed to flip the sign of 1 minus b to b minus 1, since we're taking this term to the fourth power, so the negative 1 cancels out with itself. And this is equal to, if we expand this, we get ab minus a minus b plus 1 to the fourth. And so we're actually able to find an exact value for this expression, since from what we're given, we know that ab equals a plus b plus root 3 minus 1. So ab minus a minus b plus 1 is just equal to root 3. And therefore, this expression is equal to root 3 to the fourth power, which is just equal to 9. So now we can conclude that a minus 1 to the fourth times 1 minus b to the fourth is equal to 9.
Okay.
Now we can move on to,
Yeah, now we can go to number 19.
moving on to problem. We have 5 omnoms that sit in a circle. So let's draw our 5 omnoms. And Ria chooses 2 of them at random to shake hands with each other. Then she chooses 2 more pairs of omnoms who shake hands with each other. And we want to find the probability that each omnom has shaken hands at least once. So we can kind of translate this problem to mean, so when Ria chooses 2 omnoms to shake hands, we can represent this using a line that connects 2 omnoms, and essentially we want for every omnom to have shaken hands at least once. Each omnom should have at least one edge between the omnom and another omnom. So first we want to just find the different ways that this is possible. And so essentially we have 3 edges, and we want all 5 of the omnoms to be connected to an edge. So we have, so basically we can either have, so this is basically the only case where we have omnoms, let's just say these are 1 and 2 connected, either 3 and 4 which are connected, and 5 which is connected to any of the other omnums. And so we basically we're assigning the labels 1, 2, 3, 4, and 5 arbitrarily, since none of the omnums, since all the omnums can essentially be like replaced by each other. So now we just have to count the number of ways for this to happen and divide it by the total number of ways we can choose 3 pairs of 2 omnums. So we can start with the total number of ways. So in this case, we have 5 choose, 2 ways to choose any 2 omnums from the 5 omnums. And since Rhea does this 3 times, and she is allowed to repeat omnums, the total number of ways is just 5 choose 2 to the cubed. So 10 cubed, or 1,000 total ways. Okay, so now what we can do is we can find the number of ways for the omnums to all have shaken hands at least once. So we can just start by considering the omnum which shakes hands with 2 different omnums. So in this case, we would have omnum number 4. So there are 5 different ways to choose this omnum. Then we're basically left with 4 other omnums, and from these 4 omnums, we want to first choose which 2 omnums this omnum is connected to. So there are 4 choose 2 ways to do this, and then that just leaves the other 2 omnums connected. So in total, we have 30 ways for this to happen. Okay, so thirty over 1,000 for each omnum to have shaken hands at least once.
Okay, so it looks like we have some connection issues. So I'll go on to number 20 for now. So in this problem, we are given this 3D geometric figure. And so in basically any case that you're given this kind of 3D figure, it's often best to take cross sections because we know how to deal with 2D shapes, circles, triangles, squares more easily than we do in 3 dimensions. So we have a sphere on a cone, and so let's slice it right down the middle. And so what we're left with is this. So here we have a circle, and then here I've drawn the radius and then the height. So the height will go all the way up here from down here. So we want to find that length in the ends. So let's write down what we know. The radius is 5. And then the height of the cone is 7. So that means NA is 7. Okay. And we also know the radius of the cone is 3. So NB is 3. And CN is also 3. Well, once again, our 3, 4, 5 triangle returns because this O and C is a right angle, O and B is a right angle. So this must be 4. So that tells us that OB, ON, and NB. So now there's one length we need to know. We need to know N down to the bottom of this circle. Well, what is this value? Well, the radius of the circle is 5. So that means O to this length is 5, and O to N is 4. So that means this must be 1. So now, using this information, we now extend this. Well, this is just another radius, so we know this is 5. So our height is 5 plus 4, and then plus this height, which is 7. So 5 plus 4 plus 7 is 16. So the box, whatever box is containing it, must have height 16. Okay, moving on to number 21.
Okay, so number 21 asks us to find the remainder when 2 to the 2022 is divided by 44. So first we can factorize 44 as 2 squared times 11. And so by the Chinese remainder theorem, all we have to do is find the remainder when 2 to the 2022 is divided by 2 squared and 11 separately, and then we can use these two to find the remainder when 2 to the 2022 is divided by 44. So it's pretty easy to see that 2 to the 2022 is congruent to 0 mod 2 squared, or mod 4, since 2 to the 2022 is clearly a multiple of 2 to the 2. And so now we just have to look at 2 to the 2022 mod 11. So by Matt's little theorem, we know that any number that's relatively prime to 11, let's call this A, when this is raised to the power of 10, it's congruent to 1 mod 11, since 11 is a prime. And so we can apply this fact here, and we can break 2 to the 2022 into 2 to the 10 raised to the 202nd power, and then times 2 squared, mod 11. And this is nice because we know that 2 to the 10 is congruent to 1 mod 11, so this entire term becomes 2 squared, or 4 mod 11. And so now we know that 2 to the 2022 is congruent to 0 mod 4, and it's also congruent to 4 mod 11. And if we combine these two facts, this tells us that 2 to the 2022 is congruent to 4 mod 44, since this is congruent to 0 mod 4 and 4 mod 11. Yeah, so that's basically your answer. Answer is a remainder of 4.
Okay, let's go to number 22. So in number 22, this diagram is partially incomplete. And so it tells you there's actually 5 circles and 2 lines. And so we know that every circle is externally tangent to both lines and both all of its adjacent circles. So in reality, it looks something like this. Of course, this diagram is not to scale. And so, of course, these points are also tangents, but it's kind of hard to draw like this. So now we want to find the product of these radii. So in order to do this, there's something important that we need to prove, and some of you may have noticed this during the exam. So I will erase this first, and then let's go down here so we have slightly more space. So when we have these lines and let's say these consecutive circles that are also externally tangent, we can actually prove that their radii are in geometric series. And so I will show how to do that. So let's first drop the radius to the tangents. So now we have something that looks like this. So let's say A, B, C, right? Sorry, B, C. And so those are the radius of our three circles. So now let's try doing some work with similar triangles in Pythagoras. So let's say this length is actually x, and it doesn't really matter. This is where the lines intersect. So this length from Pythagoras is actually a plus b squared minus a minus b squared, right? Because if we drop this, we make a rectangle here. And then now this length is b minus a, or a minus b. When you square it, it doesn't really matter. So when this length is equal to this length, so we can use Pythagoras, and we do that, and we get that this length is actually roots of, sorry, not 2, it should be 4ab. And similarly, this is root 4bc. Well, now using similar triangles, or, well, in this case, similar quadrilaterals, this length over this length equals this length over this length. So root 4ab over b is equal to root 4bc over c. And so if we simplify this, this is actually 2 times root a over root b, which we know is equal to 2 times root b to root c. Now this is the characteristic of a geometric series, but if you're not convinced, you can just cross multiply. So 2 root ac equals 2b, cancel out the 2's, ac equals b squared. And so b is the geometric mean of a and c, which is the definition of a geometric series. So now knowing that, let's go back up here. If in the middle we have, if in the middle we have 3, on one end we have 3 and on one end we have 75, then the center must have a radius of, it's 25, it should be 15. Oh, sorry, yes, it should be 15. And so here is 3 root 5, and here is 15 root 5. And so this is our geometric series. And so the product of these three, of course, then is 15 times 3 times 15 times 5, or 15 cubed, which is 3375. Okay. Now let's go on to number 23. Sorry, give me a second. Yes, sorry about that. Okay, so number 23. So we know that 2 TV shows are both scheduled to run tonight, with Math Jeopardy starting at 7 p.m. and the other at 7:30 p.m. Both last 1 hour. So let's draw a timeline. So 7 o'clock is here, and then we'll have an hour, approximately 1 hour here. And so we'll partition it by every 10 minutes. So that is our timeline. So 7, 8, and we know another show starts here. This is show number 1, and show number 2 is approximately here. So we'll partition again. So with that in mind, we know both shows also will run a 10-minute ad break. And so it can't be within the first 10 minutes or the last 10 minutes of each show. So this is all safe zone. No ads will run there. And we want to know, what is the probability that show number 2 here will be running programming? So not an ad break, but it also has to be running during the entirety of Math Jeopardy's ad break. So let's evaluate where Math Jeopardy's ad break could be. So if, we'll consider by start time because it's slightly easier. If we evaluate by the start time, if the ad starts here, well, Om Nom Stories hasn't even started yet. So this is not good. Same here, same thing here. And basically, if the ad break starts anywhere in this range, there will always be a tiny bit where omnum stories has not started yet. So this is all no. That's bad. Well, where else could it start? It can start here. It could start here, etc. Right? So, but it can't start here. So it can only start within this range. Because if it starts after this range, it'll run into this, and we know it's not valid. So sometime in this range. So now we have to ask, what's the probability now that omnum stories will be running, that omnum stories add will now intersect with this, with Math Jeopardy's add. So let's say our add is here. I'll mark it in a different color. Let's say our Math Jeopardy add is here. Well, obviously, if omnum stories add starts beyond this point, they'll never intersect, right? And so this part is no intersection, and we know that. So within this range, well then what's the chance of intersection? So in reality, we can use geometric probability to find this out. So if we know this time is 8:40, and this is 8:30. So 8:30, 8:40, and 8:50. So 30, 40, and 50. And then likewise on this axis. So if Math Jeopardy starts, we know Math Jeopardy can't, omnum stories add break can't start until 40. So this is all no-go. And same thing for Math Jeopardy. Its add can't start here. So in reality, the only range in question is actually this. What's the probability here? Well, let's think. If Math Jeopardy's add break starts at 30, so here, it will never intersect, right? So it'll always be good. So everything here is all good. But on the contrast, if it starts at 40, it's certainly going to intersect with omnum stories add break, which is bad. So there's nothing up here. So in reality, what we can do is, we know that the probability must be linear, right? Because as you slightly shift Math Jeopardy's break over, the probability will slightly decrease. So in fact, you don't even have to draw this out. You can just tell that no matter which way this triangle is, it's a 1/2 probability. So if it falls within this range, it's a 1/2 probability. So now let's go back and check. Well, in order for omnum's add break to be within this range, like we had assumed, its start time must fall between 7:40 and 7:50, whereas the entire range is anywhere from 7:40 to 8:10, which is a 30-minute range. So 10 out of 30 minutes is this like hypothetical area, which is one third of the entire region. So we multiply those probabilities to get 1/6. So now 1/6 within this even bigger probability of what's the probability that Math Jeopardy's add break is in this range to begin with. And once again, this is 1 out of 3, as we can see up here. 1, 2, 3. So this is 1 out of 3. So 1 out of 3 that it's good. And then times, well, this is a probability that's bad. So 5/6 that it's good. Times 5/6 equals 5/18. Okay. Now let's go on to number 24.
Okay, so for number 24, we're given a monoquadratic polynomial p of x, where a is the sum of the distinct positive integer roots. So we can write this as p of x is equal to x squared minus ax plus b. Since by Vieta's, this polynomial has sum of roots a. At the equation p of x equals a has two distinct roots whose product is a. So we can represent this as x squared minus ax plus b equals a has two distinct roots whose product is a. So if we move this a to the other side, we have that x squared minus ax plus b minus a is equal to 0. And so this is another monoquadratic polynomial, and by Vieta's we know that the product of the roots of this equation is just b minus a. We're also given that b minus a is equal to a. So this just tells us that b is equal to 2a. And so now we can rewrite p of x as x squared minus ax plus 2a. So now if we let the roots of p of x equals 0 be r and s, we know that r and s are distinct positive integers, and we also know that r plus s is equal to a, and r times s is equal to 2a. And this again comes from the Vieta's relations that we have from this quadratic. And so we want to solve for a, but we also want to use the fact that r and s are positive integers. So one way we can do this is we can see that we have this relationship as 2a is equal to rs, and it's also equal to 2 times a, or 2 times r plus s. And so now we can rewrite this in a form where we can directly use the fact that r and s are positive integers. So as you can see, if we add 4 to both sides of this equation, we can factor the left-hand side as r minus 2 times s minus 2 is equal to 4. And because r and s are positive integers, r minus 2 and s minus 2 are also positive integers, which means that r minus 2 and s minus 2 are both factors of 4. And also because r and s are both positive, we know that if we have a pair of factors like minus 4 times minus 1, we know that one of r and s are going to be negative, so these cases, we can ignore these cases. And so we can just list out the different ways to write 4 as a product of 2 positive integer factors. So because 4 is equal to 2 squared, we have just 4 times 1, 2 times 2, and 1 times 4. And we see that these first and last cases are symmetric, so we can just focus on these two cases. So the first case gives us that we have r and s, or the roots are 6 and 3, and clearly these satisfy all the criteria. And the second case gives us that r and s are 4 and 4, which are not distinct. So this is an extraneous case. And yeah, so this basically gives us that our two roots are 6 and 3. And so if we look back up here, we know that r plus s is equal to a. So we just have that a is equal to 6 plus 3 or 9. So our final answer is a is equal to 9. Moving on to problem 25. So we have a function f of n, which given a positive integer n outputs the exponent of the largest power of 3 that divides n. And we want to find the value of f of 1 plus f of 2 plus all the way to f of 99 plus f of 100. So we can think of this as finding the powers of 3 that divide each of the numbers from 1 to 100. So instead of looking at the n that goes into each function, we can instead look at the powers of 3 that go into the numbers from 1 to 100. So we can start from the largest power of 3 that divides any number from 1 to 100. And you can see that 3 to the 5th power is greater than 100. So we don't have to consider anything greater than any power of 3 greater than 3 to the 5th. So now we look at 3 to the 4th, or 81. And we can see that 81 is the only integer between 1 and 100 such that 81 divides the number. So in this case, we have 1 that contributes to the total sum. Now we look at 3 to the 3rd power, or 27. And you can see that there are, in this case, we have 27, 54, and 81, which which give us 3 numbers that contribute to this sum. And so next we can look at 3 squared, or 9. And in this case, we have the numbers 9, 18, 27, etc., all the way until 99. And this gives us 11 more numbers that contribute to our total sum. And finally, we can look at 3 to the 1st power, which is just 3. And in this case, we just have all the multiples of 3 less than 100. So in this case, we just have 33 additional numbers. And if we look at the other powers of 3 to the 0th power, while every number from 1 to 100 is a multiple of 3 to 0 or 1, this doesn't contribute any amount to our total sum, since f of n, in this case, 3 to 0 will just contribute a sum of 0, which doesn't affect our total sum. So in total, we have that f of 1 plus f of 2 plus all the way to f of 100 is just 1 plus 3 plus 11 plus 33, which is equal to 48. So this is our final answer, and the sum of f of n for n is from 1 to 100 is 48.
Okay, now let's move on to number 26. So, find the largest integer n such that 9x plus 10y equals n has 21 solutions where x and y are positive integers. So, the first thing we want to do is think about what this means. So graphically, if we have something like this equation looks like this. Something like this, depending on the value of n. The bigger n gets, the further out the line goes. And so 21 solutions means lattice points. There must be 21 lattice points. So I want to find the first line that intersects 21 of these lattice points. Well, let's consider what these consecutive lattice points really are. If we have a point AB that satisfies the equation, what's the next A that will work? Well, if we increase A by 1, that won't work. What will will we decrease b by? We have to increase a by 10, right? Because that contributes a sum of 90. And then that sum of 90 can then be compensated when b decreases by 9. So in reality, the next solution then is a plus 10 and b minus 9. So given that, then let's just set a as small as possible, right? Because we want to minimize n. So 1 and, well, something. We don't know what it is. But after 21 solutions, this is solution number 1. To get to the 21st solution, we're going to have to add 20 copies of this 10. So that will be 201. Okay, so, well, let's just set b to be 1 here, right? Because it's not too important what b is, and we want to minimize n. And so if we go backwards, 20 solutions, well, that's increasing b by 9 20 times. So this is 181. And so, well, we have now 2 points on this line. And so it doesn't really matter which one we plug in. We just plug in whichever one. We have 1809 plus 10. So our final answer is 1819. And we can actually just plug in this as well, and it gives us the same value, thus confirming that this is the smallest. And if you want to really be safe, just check n equals 1818, and you can find the number of solutions, and it'll be 20. Okay, all right, moving on to number 27. So 27, when I was writing number 27, my idea was to test partitions, but it evolved into something slightly different. So when we have a complicated word problem like this, and we actually consider the wording of this problem several times, this is actually probably the 4th iteration, you want to decode what the problem is asking very clearly. So we have 7 islands that are floating around here. 1, 2, 3, 4, 5, 6, 7. And somehow these islands are connected, and each island has exactly 2 bridges coming out of it. No more, no less. And even more so, this is possible. So you can have 2 bridges running between the same pair of islands. And so we define an archipelago to be a set of islands that are all connected, right? So you can, if we were to write this as like a friend group, this would be considered a friend group in like a problem where friends are connected or somehow. So we want to find the probability that they're all part of the same archipelago. So what does that imply? Well, let's deconnect our bridges. Let's pick this island. Let's connect it to 2 islands. First step, without loss of generality, it doesn't really matter what we connect it to. Okay, well this one, we can only connect it to 1 more island, right? And if we connect it to this island over here, well, we'll have sealed off this archipelago. Nothing else will be able to connect because every island here has 2 bridges. So that's not valid. So let's just pick another island. Well, same thing. This can't connect back here. So must go here. And, well, no, this can't go back there. So we just pick another unused island. And, well, just keep going. Eventually, you'll notice that this forms a cycle. So now we need to evaluate how many ways can this cycle be formed. Well, I kind of alluded to this just a moment ago, when we can cut off this cycle a little early. So we could have a cycle of 3 plus a cycle of 4, right? And so we'll now have 2 separate archipelagos. Oh, sorry. We could have an archipelago of 2 plus 2 plus 3. That's another possibility. We can have an archipelago of 5 plus 2. That's another possibility. And of course, 7, right? So now how many ways can this archipelago form? Well, obviously if you have 2 islands, there's only one way to connect them into an archipelago. And if you have 3 islands, same thing. There's only one way to connect them. So can we derive a closed form expression for this? And it turns out we actually can. So if we thought about how I constructed this earlier, I just picked 1 at random, right? So n factorial, we were just ordering them, kind of. But now we have to correct for a couple of things. First is rotation, right? It doesn't really matter which one you start on, as long as you go in the same direction, right? As long as your cycle continues around like this. But at the same time, what if you just go in the opposite direction? The bridges are bidirectional, so it doesn't matter which direction you travel, as long as it's a cycle. So we have to divide by another 2. And so this, in reality, is now our new closed form expression for an n archipelago. How many ways can you form an n archipelago? And if we want to write it as a closed form, it is just n minus 1 factorial over 2. So this actually fits this 3 archipelago perfectly. 2 is just a slight exception. Okay, so now that we've got this, how many ways can we split up an archipelago? Well, 7, we have to use all the islands, right? So this is just a 6 factorial over 2, which is 360. In a 5 plus 2 archipelago, well, 2 is just 1. How many ways can you find a 5 archipelago? That's 4 factorial over 2, 12. So there's 12 ways to distribute the islands within the archipelago, but then we have to actually choose the 2 islands to be separate. So it's 7 choose 2. 7 choose 2, of course, is 21. So 12 choose 21 is 252, I believe. Okay. Now, 3 plus 4. Well, now we just do 7 choose 3. And then 3 archipelago is 1, and the 4 archipelago is 2. And we can find this down here. 4 archipelago is 3. And so this gives us a total number of 210 ways. 105 ways. Okay, now 3. Well, let's pick 7, choose 3, and then with the remaining 4 islands, just pick 2, right? And then multiply by, well, there's no actual ways to organize our islands within each archipelago. So this case gives us 7 choose 3 times 6, which is just 105 again. Okay. And then we have to divide by another 2 because there are 2 archipelagos here, and these 2 can be swapped around. So we divide by 2, and that gives us the 105 here. So now let's add everything up. The total number of cases is 822. And once again, the number of valid ways is 360. Reduce this, and we get 60 over 137. Okay, moving on to number 28. So when I was writing 28, my goal was to, I guess, test on AMGM. So AMGM is the idea that if you have A and B, their arithmetic mean, A plus B over 2, has to be greater than or equal to their geometric mean. So, given that, let's try approaching this problem this way. So let's draw what's going on. So we have some kind of miniature racing hamster that goes at the speed of 1 meter per second. However, it's not good at turning, so it takes x squared to turn through an angle of x degrees. So let's say we're working with a square. Well, it takes 1 meter, 1 second. But then it has to turn through 90 degrees. So, sorry, it doesn't have to turn through, yes. It has to turn through 90 degrees this way, which is 90 squared time. And so it has to do this 4 times. So let's try to write this in closed form. So let's consider the straight lines first. If you have a n-gon, you'll have n sides, each of length 1. So you'll have n total straight length. And then now for the angles, well, you have n turns, right, because you have n vertices. And each angle's turn is 360 over n. Now the reason this is because no matter what polygon you choose, when you go around the track, you'll make 1 full turn as you return to your original spot. And so those turns are equally distributed on a regular polygon. So now we just square the angle because it's x squared. And then this is our final expression. Now, this looks very nice for AMGM because a plus b is greater than or equal to 2 root ab. And in fact, equality is achieved, or a minimum in the arithmetic mean is achieved, when a equals b. So that means n equals 360 squared over n, which means n equals 360. And this kind of makes sense, right? As you increase your sides, you're increasing this value, right? You have to travel more straight length because the perimeter increases. But your angles get very small. When your polygon gets very big, it almost becomes like a straight line. And so as that angle decreases, x squared decreases. And x squared kind of decreases faster than n. And so there's some kind of minimum value there. Okay, now let's go on to 29. 29 is, in my opinion, a very fun problem because if you play around with it a little, this is a very fun realization to find. So the idea is that when you have a laser, it will bounce off in order to preserve the in order to match the angle. So basically, if you draw this vertical here, it's symmetric across here. So that angle is equal to that angle. However, that means that let's say you want to reverse this and you flip it over the edge. So instead of the laser bouncing, let's say it goes right through the wall. And so that means that we can actually find that the laser's path, the laser's would-be path, is actually just a straight line when it's allowed to pass straight through the wall. So this corresponds exactly here. It's a complete reflection. So no matter what laser problem you find, if you reflect the boundary over itself, over and over and over, so you have more squares on this side, keep going, like this, the laser will just keep going. And when it hits a corner means when it hits any one of these squares' vertices. And in fact, you can quickly find that it actually will hit this one because this point is on the y equals 3 line right here. And so in that regard, we know that it will pass through 1, it will bounce once here, 2, it'll bounce once here, and 3, it'll hit the corner. So it'll reflect 2 times before reaching the corner of a square. Okay, moving on to number 30. So 30 is a very difficult concept. It's based on the idea of states. And the reason it's called states is because, well, you have various states in the problem and they link up in different ways. So let's figure out what those states mean. So Ethan has some number of points of more or less than Stephen here. So the game is over if one of them has 2 or more points. So let's say ET2 means that Ethan has 2 more points than Stephen. That means he's won for sure, right? So we'll define EP to be the probability that Ethan wins from that position. So if Ethan starts with 2 points, he'll automatically win. If he only starts with 1 point above, well, what does that mean? Well, on the next turn, let's say he wins. He has a 4/5 chance to win the sorry, not 4/5. He has a 2/5 chance to win the points because he's 1 point above. And if he wins, then he'll go to E2, right? Because then he'll have 1 more points. But if he loses, he'll then go to E0. The game will be tied. And so we can define these actually similarly. E-2 is obviously 0 because he's lost. And here this is 3/5. E1 plus 2/5. E minus 1. And here is 4/5. E0. And 1/5 E minus 2. And here we have 5 equations, 5 variables, so it's possible to solve this. It's not too hard, but in the interest of time, we'll probably just move on. Basically, the idea is you substitute in here, and now you have 3 equations, 3 variables. So E1 in something constant time plus E0, E-1, some function of E0, and then you plug it into here. And then now you have an equation E0, and then you solve for E0. And so the end results is that Ethan has a 3/4 chance of winning the game. So E0 is 3/4. Okay, so that's everything on the individual rounds. So we'll now go to the bonus questions. So the bonus questions, for those that are not familiar with this setup, it is inspired by a mobile game. I forget the name, but there's these colored lines that you connect, and so we'll just kind of walk through this. So, well, green looks like the nicest to connect here. Well, we could connect it like this. So what happens if we connect it like this? Well, if we connect it like this, then where would blue go? Blue would have to go around. But then this red dot is trapped. So it can't be like this. So green must somehow go around this blue dot. So this blue must connect like this. Now this red, therefore, only has one option. It must go down like this. But it also has to give space for the yellow, right? Because the yellow's option now is only go down. So red must now go around, and yellow, and so forth. And basically, it'll connect like this. And yellow, this. And green, therefore, now only has space like this. So this is just a fun puzzle. So the answer is yellow. Okay, moving on to number 2.
Number 2 asks for the number of ways there are for Audrey to rearrange the letters of HMI so that the string HMI never appears. So for this problem, we'll be using complementary counting since it's easier to find the number of ways to rearrange the letters such that HMI does appear and subtract this from the total. So first we can find the total number of ways to rearrange the letters of HMI. So since we have 2 H's, 2 M's, and 2 I's, essentially the total number of ways to rearrange the letters of this string is 6 factorial since we have 6 total letters, and then divided by 2 factorial cubed, since there are 2 factorial ways to rearrange H, M, and I. So in total, this gives us 90 rearrangements of this string. So now we want to find the number of ways to rearrange the letters such that HMI does appear. So what we can do is we can treat the string HMI as its own letter. So let's call this X. So now we have to find the number of ways to rearrange X HMI, and yeah, so in this case, we basically have 4 factorial or 24 total ways to rearrange the string. However, this does overcount one case since it is possible to have HMI as a possible rearrangement, and this is accounted for twice when we have this HMI as X and this HMI as X. So therefore, we want to subtract 1 to account for this overcounting. So we have 23 actual ways for the string HMI to appear. And so in total, we have 90 minus 23 since we're going to take out the rearrangements that do have HMI. So in total, this gives 67 ways to rearrange the letters of HMI so that the string HMI does not appear. Now moving on to problem 3 of the bonus. So we have two sets A and B that are both subsets of the set that contains the integers 1, 2, 3, 4, 5, 6, 7, and 8. And so we're given that the size of the union of the two sets is 5 and the size of the intersection of the two sets is 0. So we can represent this on a Venn diagram where we have this is A and this is B. So we know that the size of the intersection of the two sets is 0, which means that there are no elements that belong to the intersection of the two sets. And we also know that the size of the union of the two sets is 5, so in total in this area and in this area, we have a total of 5 elements. So first, let's find the number of ways to choose these 5 elements. And this is just 8 choose 5 or 56 ways to choose which elements belong to at least one of A or B. And now we have 5 elements, and we want to split these 5 elements up between A and B. So for each element, it has a choice of either belong to A or belong to B. So that gives 2 choices, and since we have a total of 5 elements, this is a total of 2 to the 5th power, or 32 number of ways to split up these 5 elements. So in total, there are 56 ways to choose which 5 elements times 32 ways to split up these 5 elements, ways to choose A and B. And this multiplies out to 1792. Okay, now moving on to number 4. So we define a number as nice if the number is composite and not divisible by 2, 3, 5, or 7. And we want to find the first 5 nice numbers. So listing out the primes that are greater than 7, we have 11, 13, 17, 19, and so on. And so for so we simply want to find the first 5 nice numbers. We want to make these nice numbers as small as possible. And for a number to be composite, it has to have at least have more than 2 factors. So we can start by just constructing some small nice numbers. So we have 11 squared, since this is this just takes the 2 smallest prime factors we can have, and this gives 121. And so next we have 11 times 13, or 143. And next we have 11 times 17, along with 13 times 13. And as you can see, we actually have 13 times 13, or 169, is less than 187. But combined, these give the first 4 nice numbers. And so now we just want to find the fifth nice number. So we'll either have 11 times 19 or 13 times 17. And so if we just multiply these two out, we have 209 and 221. And it turns out that this is actually less. So now we have our first 5 nice numbers: 121, 143, 187, 169, and 201. And so we just take the sum of these 5 numbers, which should give an answer of 829. Okay, now moving on to problem 5. So in a distant land, 2 slugs are worth 5 bugs, 10 grubs are worth 6 bugs, and 8 bugs are worth 9 bugs. And we want to find how many slugs 150 grubs are worth. So essentially this is just a unit conversion problem, and we just want to keep track of which units we're working with. So we know that we have 150 gubs and we want to convert this to slugs. So we know that 10 gubs are worth 6 slugs. So we convert this to slugs. So now we have our units of gubs canceling out, and we're left with 150 times 6 over 10 slugs. And now we know that 8 bugs are worth 9 bugs, so now we convert bugs to bugs. So we have 8 bugs are equivalent to 9 bugs. And now our units of bugs cancel out, so we use our final piece of information that 2 slugs are worth 5 bugs. So converting the bugs to slugs, we have 2 slugs are equivalent to 5 bugs. And so the units of bugs cancel out, and we're left with a unit of slugs, which is what we want. So in total, we have 150 times 6 over 10 times 8 over 9 times 2 over 5 slugs, and multiplying all of this out and simplifying, we're left with 32 slugs. So now we can conclude that 150 grubs are worth 32 slugs.
Okay, all right. That concludes the individual round in its entirety. So we'll take another 10-minute break and then we'll begin on the team round. And so thank you to everyone who is sticking around. This has been quite lengthy, but we are almost near the end. So thank you, and we'll be back in 10 minutes. Okay, alright, welcome back. So we will now go through the team round questions. So, firstly, number 1, what is the GCD of all natural numbers whose digits are all even and identical? So, natural number means it must be a positive integer, so it must be 1 or above, and all the digits must be even or identical. So let's just list those numbers. So 2, 4, 6, 8, 22, 44, and so on. And you can see the pattern. Well, first thing to notice is, well, 2 is the smallest number. The GCF, this was corrected to GCF during the real exam. The GCF cannot be greater than the smallest number. So it can only be 1 or 2. Well, can it be 2? Well, in order for the GCF to be 2, all the numbers have to be even. But if all the digits are even, the number surely must be even. So therefore, the answer is just 2. Okay, moving on to number 2. A rectangular prism has a space diagonal of length 15. What is its maximum possible volume? So this goes back to the AMGM idea that I mentioned previously. To save time, we aren't going to go over it, but basically using that AMGM principle, you can find that the space diagonal is longest when this prism is in reality a cube. And when it's a cube, the three side lengths are the same. So the space diagonal has a length of, well, we can find out. So if this is our cube, we have a face diagonal here, which is s root 2. We can find that easily because it's a 45, 45, 90 triangle. And this is s, and this is another right triangle here. And this is the space diagonal is its hypotenuse. And this we can find is s root 3. So if s root 3 is 15, then s is 5 root 3. And so its volume, therefore, must be 375 root 3. Okay, moving on to the next question. So in this question, we have two separate roads to tile. So basically, road number 1, we only use 2-meter blocks. So at the 2-meter mark, there's a seam, 4, 6, yada yada yada, all the way down to 50. So now we have another road, which we can only tile with 3 and 5-meter blocks. It asks, across all configurations, how many seams between the blocks will line up? So if we have our second road here and some amount of tiling, some will eventually line up. And we want to count the number of seams that line up across all configurations. So let's figure out those configurations. Well, notice that because 3 and 5 are both odd, no matter how you tile the 5s and the 3s together, it will always be every other block will line up, right? Because you'll have an odd length and then an even. And then that even will match to somewhere here, perhaps 8. And odd, even, odd, even. So that means that if you have a tiling with M 3-meter blocks and N 5-meter blocks, that means that the total number of seams that will line up is in reality M plus N, M plus N over 2, minus 1, because we don't want to count the edges. So given that, then let's count how many ways we can tile it. We know 3m plus 5n has to equal 50. So what are the ways? It could be 0 and 10, or it could be 5 and 7, or 10 and 4, or 1 and 15. And so this is kind of similar to that 9x plus 10y equals n problem. So then, given this information, how many ways are there to configure these m 3-meter blocks and n 5-meter blocks? Well, you have n plus n blocks in total, and you should just choose m or n slots, it doesn't matter, to be whichever corresponding block it is. So we get m plus n, choose m. So the total contribution of each configuration is m plus n, choose m, times m plus n over 2 minus 1. And so we'll plug in each of these 4 scenarios into here, and to save time I won't do the computation right now, but you can find that the answer is 10,000 and 82. Okay, moving on to the next question. So we have this C-shaped polygon, and we're going to cut it using some kind of line. And then this line is going to divide the area in half. So whenever you have a problem that doesn't quite have, like, has more freedom than the solution allows for, you can just pick the lines yourself. So the line, I'm going to pick a horizontal line. Very simple. And then a vertical line. These are very easy, so this will make it easy for me. And so vertical line, horizontal line obviously must go through y equals 3, right? It's vertically symmetric. But x is slightly trickier. Let's figure out what the x line is. So we have, let's say, a distance of x here, and this must be 4 minus x. The area of the entire C-shaped polygon is 20. We can count grid boxes on this diagram, or we can find this quite easily. So if you have 20 total, that means 10 must be on this side of the line. Well, if the height is 6, and this is just a rectangle here, well, x must be 5/3, because 6 times 5/3 is 10. So if x is 5/3, then this line is x equals 5/3. And so these lines quite easily give us this intersection point. And then you can say, well, what if this line didn't, what if you had a diagonal line that didn't necessarily pass through this point? It turns out that it necessarily will. And so it's a little more complicated to prove, but every line that splits the area in half will pass through this point, which we can call the center of mass. And so if you were to cut out the shape on paper and hold it by one point at this point, it would balance itself. Okay, now moving on to the next question. So we're given this complex looking polynomial, and we want to find the smallest possible value of the sum of the squares of the roots. So what does that mean? Well, let's see. Sum of the squares of the roots. Let's try and decode this first. Let's say our roots are r, s, and t. Sum of the squares is r squared plus s squared plus t squared. In order to find this value, it's very easy to do this with Vietas. So Vietas says that r plus s plus t is equal to the negative of this value, and that rs plus st plus rt is equal to this value. And so, in fact, if we square this and then subtract 2 times of this, we'll get this expression. And you can show this convince yourself of this. So, given this, well, what's suspicious about these? Well, this is just twice this. And it's kind of messy to write out, so I'm just going to substitute. Let's say this is 2a, and then therefore this is a. So the sum of the roots is a, and this pairwise product is 2a. So this suggests that the sum of this value is equal to a squared minus 2a. Okay, well, what does that mean? We want to minimize this. When is a squared minus 2a minimized? Well, this is a parabola, and a parabola that opens upwards. So therefore, it must have a minimum somewhere. And in fact, we can factorize it, or however you wish, to find that that minimum occurs when a equals 1. So when a equals 1, this is minimized, right? And so it has a minimum value of minus 1. However, we have to go back to this expression. Can k plus 1 over k plus 2 in reality equal 1? Okay, well, let's try and find out. So, this value for positive k, well, AMGM, right? We've seen this previously. This AMGM, this must have a minimum value of 2. And so if this is the minimum value of 2, has a minimum value of 2, then this, then adding this, the minimum value in reality is here is 4. And it can only get larger, which means on this parabola, it can only get away from this point, which means it'll only get larger. Therefore, 4 is the best option here, and 4 corresponds to a sum of, sorry, I misfactored this. Yes, it'll correspond to a minimum of 8. Okay, moving on to the next problem. So we have a cube, and there's an octahedron inside it. So an octahedron basically is two pyramids stuck together. Two square pyramids stuck together. And so it looks something like this inside. So it's some kind of this kind of diamond shape inside. So let's actually, once again, try and slice it open. So we'll first handle this step, and then we'll put the cube inside. So if we want to find the volume of this octahedron, let's consider this. Let's slice the cube open kind of horizontally in the middle, right there. If we take this cross section, we'll find that the octahedron's center is a square that is just diagonally rotated inside. And so if the square has a side length of 2, then the side length of this octahedron is root 2. And so the area of the octahedron square is 2, and its height is 1. So it has two pyramids of base 2 and height 1, which gives you a total volume of 4/3. So the volume went from 8 to 4/3. The octahedron has a volume of 4/3. So now, given that, then now we need to try to find the volume of the next cube inside. So this is actually slightly trickier, but we can notice that when we have a pyramid, those cubes must occupy the centers of the centers of the equilateral triangles that are formed. So we'll just try to find this length. So let's draw these heights. So if you notice, they connect the midpoints of these two segments on the square. And we know from here that this side length of the octahedron is root 2. So this is root 2 over 2. And so this is 1. Well, we also know that in the center of a triangle forms a 2-to-1 ratio. So 2x to x ratio from the vertex to the intersection point with the other edge. So if that's true, then we can use similar triangles. And since this is 1, this must be 2/3 of this value. So this length is just 2/3. And those 2/3, this 2/3 must be the edge of the cube, right? Because this is the cube. If we extend it kind of downwards, we can visualize where that cube would extend. So our smallest cube's side length is 2/3. So its volume is 8/27. So cube 1 is 8, has a volume of 8. Cube 2 has a volume of 8/27. And if we keep infinitely going, we can use propagate this idea, and we'll have a common ratio. So with that in mind, let's solve this geometric series. So 8 is the starting term, and the common ratio is 1/27. And the formula for this is 8/1, 1/1 minus 27. And so the combined volume of all the cubes we can find to be 180/13. All right, on to number 8. Okay, so this question was a bit wordy. So basically what the question is asking is, you're simulating dice rolls, and you'll continuously manipulate the numbers on the dice until you roll a favorable amount. And so the first thing to notice is that the number of drills you will ever do will never exceed 4. The reason is, if you drill 4 times, that means after your third drill, your satisfactory value is 2. However, that means you'll have to drill through the other faces at least 3 times and then roll that face another time. But that's impossible. So if you have 1, 2, 3, 4, 5, 6, you can never roll 1 or 6 until the end. So you have to roll 3 times across here. And you can never, you have to not get a satisfactory value until that very end. That means you can only roll a 2, 3, or 4. Let's say you roll, I don't know, a 3. Then that becomes 4, 5. Well, 4 is now satisfactory, so you have to roll the 2. So now you have to drill 3 and 6. That becomes 3 and 6. but now your satisfactory value is 3. So you'll have to roll onto this 1. But that means you'll only have drilled 3 times. So that means 4 drills is impossible. And so we'll use that to casework. So let's count the number of times we drill. If you drill 0 times, this is very simple. That means you rolled 5 or more on your first try. This is a 1/3 chance. If you drilled 1 time, well, let's see. You initially get 1, 2, 3, 4, 5, 6. If you drill 1 time, well, you have to roll one of these values. That's a 2/3 chance. But let's split it up even further. Let's say you roll 3 or 4. That's a 1/3 chance. Then your dice becomes 1, 2, 4, 5, 5, 6. Your satisfactory value is now 4, so you can only roll 1 or 2. You have to roll one of these 4. That's a 2/3 chance. Alternatively, if you roll 2 or 1, well, these will increase by 1 and these will increase by 1, but these are already satisfactory, so it doesn't really matter. So you'll have 3 unsatisfactory values, and 3 satisfactory values. So this is a 1/2 chance. So combining these, we get 2/9 plus 1/6, which gives you a total probability of 7/18. Okay, now 2. 2 is a little more complicated, and you can do it. The most foolproof way is just to simulate it. So like do every single option. So the first roll, you can either roll 1, 2, 3, or 4, and then branch it out from here. To save time, I won't demonstrate it right now, but the probability you should get in this case is 47 over 216. So you can simulate this case and make sure you keep lowering your satisfactory value. Okay, now onto 3 drills. To save your time during the contest, once you find the 2 drill value, you don't need to do any further computation to find the 3 drill case. Because we know that 4 drills can never occur, we just proved that. So now, this probability plus this probability plus this probability plus this probability must equal 1, right? Because these 4 cases encompass all of the possibilities. So you just subtract these 3 probabilities from 1, and then you get here 13 over 216. Okay, now we want the expected value of the number of drills. Well, what expected value means is you multiply the probability by the value. So, and then you sum it all together. So you have 1/3 times 0 plus 7/18 times 1 plus 47 over 216 times 2 plus 13 over 216 times 3. And then your end result should be 22 plus 1 over 216. The reason we added an extra 21 here is because your dice already starts with 1, 2, 3, 4, 5, 6, which has a sum of 21 originally. So we just have to remember to add it back in the end. All right, moving on. So we know this is a geometric series. So we know b plus 12 times d is c squared. Expand this, bd plus 12d is equal to c squared. We know this is ABCD is an arithmetic series, so b plus d equals 2c, or b plus d over 2 equals c. So, well, let's plug in here. So we can plug in to find that bd plus 12d equals this squared. So this is b plus d over 2 squared. And then if we move stuff around, we can find that 12d equals b minus d over 2 squared. If we subtract bd, because we subtract bd, this will go into that product term in here, and it'll turn it into a minus. We can refactor it. So 12d is a perfect square, so let's test values of d. We can test, for example, d equals 3. Doesn't quite work. We can test d equals 3, d equals 12, stuff like that. So if we test d equals 12, well, we can find that no solution exists, right? It'll imply that b is 36, but that doesn't make too much sense. If we plug in, we can find C and A, and there's no real solution there. So let's try d equals 3. So 36 equals this squared, so 6 equals b minus 3 over 2, so b equals 15. So if b is 15, c must be 9, d is 3, a is 21. So then geometric series, we can plug in 81, 27, 9, 3, and voila, we have a satisfying condition. So let's sum up all the terms, and then we get 48. Okay, moving on to number 10. So Ria is now playing darts, and she has a 7/8 chance to hit any given dart. She throws until she misses, and the nth dart she hits earns her n points. So if she hits 2 darts, the first will be worth 1 point, and the second will be worth 2 points, for a total of 3 points. So find the number of expected points she will earn. So let's think. So if she hits 2 darts, she gets 3 points. If she hits 3 darts, she gets 6 points. So these are triangular numbers, right? And so we can express this as n times n plus 1 over 2. So this is the number of points she scores if she hits n darts. Well, what's the probability she hits n darts? Well, it's 7/8 to the power of n. But she can only hit exactly n darts, so she must miss the next one. Okay, so now, given that, let's sum it all up, right? Because expected value is the probability times the value summed across all the cases. So basically, we're summing this value across all n. Well, how can we do this? Well, let's take out the 1/8 first. We'll add it back at the end. Let's write out some terms. So the first term is, well, 0. This is our sum. And then the next term, she hits 1. So it occurs with 7/8 chance, and she scores 1 point. Next one, she hits 2 darts. She scores 3 points. And so on and so forth. Okay, well, how can we solve this? We know how to solve normal geometric sequences. But here we have this increasing constant, so how can we get rid of those? Well, let's try shifting s. So let's multiply by 7/8. So now this is 7/8 times 0 plus 7/8 squared times 1 plus ... Then let's multiply again, because there's still some constants left. You'll notice that this becomes 1, 2, so on and so forth. Equals 7/8 squared times 0 plus... Oh, sorry, my bad. I forgot a step. So we'll subtract these. So if you subtract these, 1/8 s becomes 7/8 times 1 plus 7/8 squared times 2 plus so forth. So now you have an arithmetic sequence here. So it's slightly nicer. So now we repeat the same process. Just multiply this quantity by 7/8 and then subtract again. And then, in the interest of time, I'm going to skip this part. I will just say that the final sum is 448. So after all of these steps, you can find this is 448. Okay, moving on to number 11. So evaluate the remainder, when 2022 factorial over 2017 to the power of 2019 is divided by 27. Okay, so this is a lot. So let's think about what we have in our toolbox for modulo. So obviously this power is kind of interesting, and 27 is kind of interesting. Usually problems will use 2022 because this is 2022. So the reason we picked 2017 here is because we needed to pick a prime. And the reason we had to pick a prime is because we needed to use Fermat's Little theorem. And then if you remember from previous problem, Fermat's Little theorem basically says that if you have some value to the power of 2016, when you mod it by 2017, you'll get 1 because 2017 is prime. Okay, so that will actually eliminate a lot of factors here. So that's good. It'll just become a cubed term. So this is very easy to deal with. However, what is not easy to deal with is this factorial term. So how do we deal with this factorial term? Well, it turns out there's another theorem called Wilson's theorem. Wilson's theorem says that 2016 factorial, when divided by, when modded 2017, is -1. Once again, because 2017 is prime. So, with that in mind, the top part becomes, well, canceling the 2017 out, it becomes 2022, which is just 5, times 2021, 4, so on, 3, 2, 1, times -1 to the power of 3, right? Because we can get rid of that 2016 power in the top. So now it's just -120 to the power of 3, and you can plug this into the calculator, because this is a team round, and then find that this is equivalent to 569 mod 2017. Okay, on to number 12. So number 12, very interesting shape. So the first thing you'll need to know is that is this principle that for any convex polyhedron, the number of vertices minus the number of edges plus the number of faces is 2. So we can solve this, and we know then that the number of faces is 37. At any vertex, 3 faces must meet, because these are all hexagons and pentagons, right? You can't have 4 pentagons meeting at a face. They quite literally just won't fit, because each pentagon has an angle of 108, so if you try to fit 3 of them together, you'll have a little gap, but if you try to fit a 4th one, it'll overlap completely. And you also can't have 2 faces, right? If you have only 2 faces, you won't be able to fold together a polyhedron, if you imagine the net. So that means at every face, there are 3 edges meeting. The first thing we know is that, let's say there are H hexagons and P pentagons. 6H plus 5P equals, well, the number of, we can say, edges. However, the number of edges times 2, right? Because every edge is shared by 2 faces. So the number of faces total is twice this. However, we also know that H plus P, well, is 37. So with these systems of equations, we can solve to find that H is 25 and P is 12. So there are 13 more hexagons than pentagons. And in fact, in chemistry, this shape is called the C70 fullerene. If you are curious, it is a very close cousin to the buckyball. If you've heard of that, it's just slightly elongated. Okay, we're coming into the final stretch, number 13. So we have this configuration of dots, and we want to make a triangle on it. So what are the probability that the triangle has 3 vertices of the same color? Well, let's try and construct a triangle with the same color. If we pick 3 dots of the same color, well, they're going to make a triangle, as long as they're not on the same line. If you pick 3 dots on the same line, you won't get a triangle, you'll get a line. So with that in mind, 12 choose 3 is the total number of ways to pick those three points. But there are 2 times 6 choose 3 ways to pick it on the same line. So we have to get rid of those, and this gives us 180. However, this can be repeated for each of the 3 colors. So in reality, it is 540. Okay, now let's find the total number of cases. How many ways can we make a triangle as a whole? Well, 36 choose 3. Except we now need to get rid of the cases again where it's on a line. So let's say they're all in the same row or on the same column. There are 12 rows and columns, and once again, this case is 6 choose root 3. Well, what's another case? Well, another case is, what if it's on a diagonal like this? Well, then we have to handle those diagonals, right? So there's a diagonal with 3, there's a diagonal with 4, and there's a diagonal with 5. There's a diagonal with 6, 5, 4, 3. And you can go on the other length as well. 3, 4, 5, so on, and so forth. And so on a diagonal with 6, there are choose 3 ways to make to select those 3 points. And similarly with a diagonal with 5 points, you have 5 choose 3. And so because there are 4 diagonals of every type, except the 6 ones, what you get is this. This is the total number of these diagonals that are bad. And then only 2 for the biggest diagonals. So we have to subtract those out. Now, let's subtract out a final case. And this one is the hardest to spot. But basically, if you have a diagonal like this, it has a slope of either 1/2 or 2, depending on the angle. And it will pass through exactly 3 points. So there's a number of ways, there's a number of these. Let's just take the ones with slope 2 first. We can actually trace it out. We can find that there's 4 of these diagonals on each row, and there are 2 possible rows for this. So in reality, there are 8 ways to do this, and there's only 3 points on each. So there's only 8 per orientation. However, you can also reflect it. So you can have lines like this, and you can rotate it. So you can have lines like this and like this. So that gives us 4 orientations of 8 each, which is 32 more cases to get rid of. So push it all together, and then we get a total of 6,768 cases that work. And then now we put it, divide 540 by 6768, and we get 15 over 188. Okay, number 14. So number 14 is this classic 6 game taken to a crazy level. So basically this game is you take anywhere from 1 to n sticks, and the person that takes the last stick wins. So you want to find the number of, find all of the n such that Adam will win if both players play optimally. So let's simplify this. When you have like these ridiculously large numbers, let's simplify them. Let's say you can only take either 1 or 2 sticks. So who wins? Well, if there's 1 stick or 2 sticks, well, Adam, the first person wins. So Rumi wins. Rumi will win here. Well, if there's 3 sticks, well, Rumi has to move, and then it'll go to either 1 or 2. She cannot take all of them at once, and she'll leave enough for Adam to take on her next turn. So Adam will definitively win here. Well, if there's 4 sticks, Rumi can say, oh, well, I'll just take 1 to leave 3. Now Adam is stuck, can only take 1 or 2. So now Rumi can take the remainder after that. And this is the same for 5. And we can propagate this pattern upwards, and we'll notice that Adam will only win on a multiple of 3, which is incidentally 1 more than 2. And so we can actually continue this pattern, and we can find that Rumi will always win as long as the total number of sticks is not a multiple of n plus 1. So therefore, Adam wants there to be a multiple of n plus 1 sticks. Well, that means n plus 1 has to be a factor of 3599000. Okay, now 3599000 is an incredibly ugly number, but it's chosen quite intentionally. The reason is because 3599 is very close to 3600, which is 60 squared. And in fact, difference of squares tells us that this is 60 squared minus 1, or 59 times 61. And then we add in the zeros, which is just 2 cubed times 5 cubed. So this is the factorization. Well, knowing this then, we know the factorization of this, so n plus 1 just has to be the sum of all factors here. Well, let's firstly note down how many factors there are. There are 2 times 2 times 4 times 4, which is 64 factors. Now let's try to make the sum of all the factors. Let's just ignore this plus 1 for now because it's kind of annoying. So how do we find the sum of all the factors? Well, let's write this like this. 1 plus 2 plus 4 plus 8 times 1 plus 5 plus 25 plus 125 times 1 plus 59 times 1 plus 61. And you'll notice we can pick any power of 2 here, any power of 5 here, any power of 59 here, any power of 61 here, and multiply them together, and that'll give us one factor of 3,599,000, right? So in this regard, when we multiply this product together, we've now found the sum of all the factors of this giant number. Now, we just need to subtract 1 from every factor. But we're just finding the total sum, and we know there are 64 factors. So let's just subtract 64. So in the end, our final value is 8704736. Okay, number 15. Number 15, unlike the previous problems, is a very clean problem, not a lot of computation in it. So the first thing to do is let's try and cancel something because we don't want to deal with squares. So let's divide the second equation by 4. This gives us x over 4 equals y squared minus 20y plus 100 minus 15. Okay, well, now let's add it to the first equation, which is y equals x squared minus 10. Well, we get this, and let's rearrange it slightly so that all the x and y's on the same side. So this becomes x squared minus this x over 4 plus this y squared minus this 21y. And then let's move all these constants to the other side. So these constants will end up being negative 75. Okay, this is suspiciously like a circle, right? And if this is the equation of a circle, we can rewrite it as such. In fact, we can rewrite it as x minus 1/8 squared plus y minus 21 over 2 squared equals this value. And so the center of the circle is just these values. And you don't even need to compute this because this is just the radius. This tells you the center. So the center is 1/8 and then 21 halves. And that's all. All right, so that is all the problems on the HMI 2022. So thank you to everyone for joining us today. It's truly been an honor and a great pleasure to be able to host HMI for you all. So remember that these problems were intended to be very difficult, so please don't be discouraged if they were hard for you. They were hard for every team. Our website and YouTube will be displayed on our outro screen in a minute. If you'd like further resources, there's also a place where you can sign up to receive email updates from us if you wish on HMI 2023. We encourage you to let your coach know about this site as well in case they want information for registration next year. If you have any questions, we'll stay around at this stream to answer them. But additionally, if you would like to email us, our email will also be available on that website. And we'll also stay around to answer them. And so have a great day for the rest of you, and we hope to see you at next year's HMI. So once again, thank you so much.